Okay. Okay, so today we will talk about two-dimensional wave equation. So this is the wave equation to describe a membrane, right, sitting on the xy plane here. Okay, so that so you can think about it as a membrane, a conventional membrane, and with width A and length B. Okay. And the two-dimensional wave equation is to model in the diffraction of the membrane, all right, which will vibrate vertically. So the diffraction will be called C, which is the function of the point on the membrane with coordinate x, y, and at the time t. Okay. All right. So u of x, y, t to be the vertical displacement of a point xy of a vibrating rectangular membrane okay, and this membrane is locating on the region. Okay, so R with point such that the x coordinate is in between 0 and A, and the y coordinate is in between 0 and B. Okay. Okay. At time t. Okay, so and now the displacement u of x, y, t, okay, will be governed by a two-dimensional wave equation on R, right? It's equal to c squared and t c squared, okay, is equal to t over rho. And the assumption is that the tension so of the membrane when at rest xt, and the rho is, we assume the membrane is homogeneous, so rho is the density with dimension, which could be gram per square centimeter. Okay, so that this gives us the c square. Okay. And we will impose boundary condition on the boundary we denote it as dr of the rectangle okay. Okay, so well, will be equal to 0 for all t and for all xy in the boundary. Okay, so the boundary of this rectangular membrane consists of 4 sides. Okay, so that the 1, 2, 3, 4, there are 4 sides, and we assume that we fasten the membrane, okay, of the 4 sides on the plane, so that there will be no vertical displacement. Okay, so that is the zeros. Okay, and we'll also impose and 2 initial conditions. Okay. Right. One is about the initial displacement. Okay. And about the first one is called initial displacement and also initial velocity. So this is about initial displacement. And this one is called initial velocity. Okay. So the problem is very similar to the one-dimensional wave equation we discussed before. Okay. Okay, so our job is to solve this 2-dimensional wave equation together with the boundary condition and 2 initial conditions here. Okay, so there are several steps, right? Step 1, we use separating variables. Right, so we let that the solution is a product of a function of x, y, and a function of t first. All right, so I think it's called 12.9.1. And the boundary condition 0.2. Okay, and this is 0.3, 4. Right. All right. So so now Okay, so this implies that with 12.9.1, okay. Now the second order partial derivative with respect to t becomes to be f of g dot dot, okay, and equal to c square and g plus f of y yg. Okay. Okay. So the left-hand side is just the second order partial derivative with respect to t. Okay, so because this is function of xy, so we take the second derivative of g here. Okay. Now the right-hand side is the 6 square times the sum of the second order partial derivative with respect to x as well as with respect to y. Okay, so this is here. Okay, so this is the partial second order partial derivative of f with respect to x, and this one is the second order partial derivative of f with respect to y here. Okay, and so that we have at c square and the g. Okay, so we divide c square g. So move c square g to the left hand side and move f to the right hand side. Okay, so we have f xx plus f yy and f. Okay. All right, and the left hand side depends only on t, and the right hand side depends only on x and y, so that this becomes to a constant. Okay, so this is the common result by using the method of separating variables. Okay. Okay, so from here we have two ordinary differential equations. Okay, so that we have one ODE, okay, which is g dot dot minus k c square g equal to 0. Okay, which govern the time evolution okay, of the displacement and one ODE. Okay. Oh no. PDE. One PDE. So this PDE is f of xx plus f of yy minus kf equal to 0 for xy in the rectangular region here. All right, and this PDE governs the amplitude of the vibration. Okay. at every point, right? So that so this is the, because we have vertical vibration on E. All right. So and so now to solve okay, so this gives us 12.9.5, and this PD 12.9.6. All right. So that's for this simpler PDE, we let again with the method of separating variables. Okay, so we set f to be the product of a function of x and a function y here again. All right, and so now so this PDE give us that we have Q and plus H okay. Minus K right. So so now we can move these two. Okay, for example, we can move these two to the left-hand side. Okay, the second term and the third term move to the right-hand side. Okay, and we do the proper division. Okay, so which is minus K. Okay. So you can see that the left-hand side depends only on x, and the right-hand side depends only on y. So that this is equal to a constant p. Again. Okay, so we have a constant p here. And from that, so we have so we obtain two ODEs. Okay, so the first one would be minus pH equal to 0. A, and this is 7, equation 9.7, and d square qy dy square, okay, minus k minus p and the qy equal to 0 for, so this is 12.8. Okay, so finally, by applying the method of separating variable twice, we obtain 3 ODEs. Okay. Okay. And these 3 ODEs are all second order. Okay. Now we see the boundary condition, the consequence of boundary condition. So the boundary condition okay, in 12.9.2 says that the u of x, y, t equal to h of x, q of y, and g of t equal to 0 for all t, and for all points in the boundary of the rectangular region R. Okay. Now, since G is not identical to 0, for all t, okay, so we must have, which means that for some t, g of t is non-zero, okay, so which means that the h of x, q of y would be 0, okay, for all x, y in the boundary of R. Okay, and this one, so we have, so this equation renders two boundary conditions. For the ODE so for the ODE, this one in 12.9.7, which says that H 0 is 0 and HA is 0. And two boundary condition for the ODE in 12.7.8. Which one? This one, okay? Governing the Q function. So Q of 0 is 0, and Q of B is also 0. Okay. Okay. If you examine the this equation, which means that H 0 Q y is 0 for so this corresponding to this one, okay, this side, okay, for y, okay, and H B Q y equal to 0. Oh, okay. And H x Q 0 or and H of x Q of B is 0. right? So because we have both sides, so that we have four identities. Okay. Now, because q of y cannot be identical to 0, right? If q of y is identical to 0, then f is identical to 0, and then u is identical to 0. Okay, which is trivial. Okay, and when q of y is not identical to 0, which means that for some y0, q of y0 is not equal to 0, right? So this is non-zero for some y, and so h0 is 0, and HA, sorry. And the HA is also 0. Okay, so this gives us these two. Similarly, h of x cannot be identical to 0, right? For all x in between 0 and a. Otherwise, when h of x is 0, then f of xy is 0, and then u is 0, which is trivial. Okay. Okay, so that you can find some x such that h of x is non-zero, and with that value, then q0 is 0 and qb is 0 too. Okay, so that we have two boundary conditions for this ODE and two boundary conditions for this ODE too. Okay. Now we have a lot of experience, right, to solve the equations there. And so now we consider, so to solve equation together, the boundary condition. So this boundary condition is 12.9.9 and 10. Okay, so for 7, all right, and 9. This is boundary condition, right? And this is the ODE. So maybe I say to solve the ODE in 12.9.7 together with boundary conditions. .9.9, okay. We consider that P is positive. Okay, so a general solution of, so it's okay. So now with boundary condition, this gives us A equal to B equal to 0. So a trivial solution. Okay, which is not the case we want. Right, and the second, 0. So a general solution of give us plus B, and with the two boundary conditions, okay, which means that A equal to B equal to 0. Okay, again a trivial solution here. Okay. All right, and for P equal to minus mu square, right? So when P is negative, then a general solution of equal to A cosine mu x plus B sine mu x. Okay, and with boundary condition. Okay, so that so h of 0 give us A equal to 0, and when A and the B sine mu A equal to 0. Okay. Right? So this is implies that sine mu A must be 0 if B is not equal to 0. Okay, because if B is 0, then we have a trivial solution. Okay, to things B not 0 as required for a non-trivial solution. Okay, so that this means that mu is equal to m of pi and A, where m, okay, is in, so n are all natural numbers there. Okay, because mu is assumed to be positive, so mu are all positive integers. Okay, so we have that. Okay, so similarly, right, to solve the ODE in 12.9.8, so it's about the Q function, okay, together with the boundary condition in 12.9.10. Okay. We find only trivial solution when the K minus P, is positive or 0. Okay. Okay. Oh, by the way, I have to say, so we define HM to be sine and A and pi x. Okay. Okay. So, and when k minus p equal to minus mu square, with which is negative, with mu greater than 0, a general solution of 12.9a, it's q of y equal to c cosine nu y plus d sine nu y. Okay. And now with boundary conditions, okay, we find two boundary conditions for the Q function there. Right? So we find that C equals 0, and B and the D sine nu B equal to 0. Okay. All right. So which implies that sine nu B equals 0 if since D not equal to 0 as required for a non-trivial solution. Okay, so that this means that nu is equal to n pi divided by b. Okay, and the n is any positive integer. Okay, so a solution. So we define q and y to be sine n pi y b okay is a solution of 12.9.a satisfying 9.10 with when k minus p is equal to minus m pi by b square. Okay, and also this one, all right, let me say, so a solution of 0.7 satisfying with p equal to minus m pi a square. Okay. Right. So all this, so they are our solutions. All right. So now we have p. P should be this number, and k minus p is this number. Okay. So which shows that so now with p equal to minus m pi divided by a square, and k minus p equal to minus m pi divided by b square. So we have k. Okay, so k to be the sum of these two, right? And so k equal to minus pi square and m square divided by a square plus n square divided by b square. Okay. Okay. So I think I make a mistake. So in my lecture notes, so I put a square here, but there's no square. Okay. So okay. Okay, so k is equal to minus pi square and the sum of these two squares. Okay, so yep. All right, so k is here, and the ODE are in 12.9 point. So the ODE governing the time evolution here. Governing the time evolution here. 5. Okay. Okay, becomes the G double dot C square pi square and m square a square plus n square v square and the G equal to 0. And I put square here, right? This is incorrect. So please remove the 2 here, the square. Okay? Right? Because in my note I put here, but this is incorrect. Okay? So you have to remove the square notation here. Okay. All right, and you can see that this k is positive. Okay. So we can have a general solution. So this one is a general solution. Okay, so which is a general solution. We call G sub mn t comes to E of mn cosine lambda mn t plus E star mn sine lambda mn t. Okay. All right, and where lambda mn, so the eigenvalue will be c pi square root of m squared divided by a squared plus n squared divided by b squared. Okay, for all m n in the set of all natural numbers. Okay, so mn will be positive integers. Okay, so they are positive integers. Okay, so we now find infinitely many solutions of the two-dimensional wave equation in 12.9.1 satisfying the boundary condition in 12.9.2. Okay, so that satisfying. Okay, so we have u mn x y t, which is defined to be g mn t h mx and q and y. Okay. So here is E mn cosine lambda mn t plus E mn sine lambda mn t. Okay, and the sine m pi x divided by a times sine m pi y divided by b. Okay, for all x, y in the rectangle, and for all t, again, and for all mn in n. Okay, so we have infinite many of them. And now the unknown coefficients, EMN and EMN star will be determined by the initial conditions. Okay, and we have two, right? We have two initial conditions to determine this one. Okay. All right. Okay, but in general, for a specific m, specific n, that this is solution. Okay, this is solution. We will call eigen solution corresponding to eigenvalue lambda mm may not satisfy the two initial conditions. All right, in general. Okay, so now we will use superposition principle. That means that we will use theorem 12.1.1 in section 1. Okay, so but before that, okay, so this is called, so they are called eigen function of the vibrating membrane. Okay, corresponding to eigenvalue lambda mn, which is equal to c pi square root of m squared divided by a squared plus n squared divided by b squared. Okay. All right. So this eigenfunction satisfying the boundary conditions. Okay. Because that we know the four sides of the membrane are fastened. Okay, are fastened there, so that they will not vibrate. Okay, they will stay there. Okay, for all the time. Okay, and so if we don't impose any initial conditions, then this will be solutions of the two-dimensional wave equations. Okay, about the vibration of the rectangular membrane. But so they are called F sub mn, which divided by 2 pi. Okay, so the eigenvalue divided by 2 pi will be called the vibrating frequency. It's called vibrating frequency of the eigenfunction umn xyt. Okay, right. So they are called the MM mode of the vibrating membrane. Okay, so they are natural mode. All right, over there. Okay. Okay, so now I stop here, and so we will use superposition principle to find a solution of our two-dimensional wave equations. Okay, when we impose initial conditions.